Oh, yeah, yeah, yeah. All right, so where had we gotten to? All right, let's just recall also. So then the with respect to this one-sided testing or whatever, or two-sided testing, I was just wanted to remind everybody that this if we assume the mean is equal to a particular value over here, and then we wanted to try and show, let's say, hypothesis one right here, then how would you be able to show that? Where would the sample result have to be for us to say that the mean is going to be larger than this? If we were when we're labeling this diagram? No, 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 but I mean, where on the diagram should it be? Because technically I haven't told you what the very far to the right is correct. So then if it's somewhere over here, somewhere, then this would be like a very extreme value compared to this mean possibly, and then that means it's significantly different. Therefore, we would say that maybe the initial assumption, assuming that the mean is equal to mu naught, is not correct, right? Okay, so then and then likewise, if it was if it was hypothesis two here, then we would need some value over there. Is that right? If it's hypothesis three, what would you need? What do you mean? So it has to be, how can it be on both at the same time? Why very far? Why? Why? Why does that be farther? Why? Okay, so then if we have a two-sided test, then we're going to put our alpha here on both sides. Therefore, this would be like alpha over 2, and this would be alpha over 2. As opposed to the one-sided tests, where all of the alpha would just be on one side, right? The rejection region or critical region. And then so for me to be inside of this region versus being inside of this region, right? It's definitely going to be more difficult to be inside of this region here. Is that correct? Why does that make sense? Like in terms of the hypotheses? Like why, if we were trying to say that this is greater than mu naught for the alternative in this case, and the alternative in this case is mu is not equal to mu naught, why in this case does it make sense to start saying that it should be actually harder to reject the null hypothesis? Does that make sense what I'm saying? Why would you say that though? You have any idea? If we say that here, we're pretty sure that we think that the mean is actually larger than this value, right? At least we have some idea of what's going on with this distribution. Is that correct? But in this case, what the heck do we know? Not much, right? So the thing is we can't even say if it's going to be bigger or smaller. Is that right? So then the burden of proof should be slightly higher in that case for you to reject the null hypothesis. Is that like we consider like the alpha level to be the necessary burden required that people would have to, accomplish, right? So then the thing is that alpha over 2, you have to be smaller than alpha over 2 now, right? So it's harder. So I'm just saying that that's more difficult to reject the null hypothesis. Does that make sense? Question? Question? If alpha over, well, it depends if alpha is 0 or not, I guess. Negative alpha? That's going to be a little difficult. So then there would exist some critical value here. Usually I refer to this as Z alpha star, okay? All right. So then there'd be some critical value here, which we can refer to this as the decision criteria, where that if you end up having a critical value larger, or excuse me, if my number of standard deviations for my observed sample is larger than this critical value here in this case, I would fall into this rejection region, and then we would reject the null hypothesis. Is that correct? So if Z is greater than Z alpha, right? We reject the null hypothesis. Is that correct? Any question with this? All right, then what's the answer to the first question here? Entomologist writes an article in a scientific journal which claims that fewer than 16 in 10,000 Male fireflies were unable to produce light due to a genetic mutation. Use the parameter. So this shouldn't even be here. So they want us to write the null and alternative hypotheses here. What would they be? Oh, how do you do that? How do we do this? What should we do first? Yeah, I just read it though. But what should we do first when we're attempting to determine null and alternative hypothesis? True. Okay. So the first thing you should always do is try to see if it's going to be a mean versus a proportion. And then of course, if they did something else, we'd have to know that also. But right, if we're doing mean versus proportion, right? Then what do you do? Which one of these two should I be doing first? Alternative. Why should you do the alternative? Because they have to tell me in the question what they want me to prove. Is that correct? All right. So we need to read the question to determine which thing they're trying to prove here. What do they say? Or what are they trying to prove? What would you say? Oh, wait, first, excuse me, is it mean or proportion? Proportion. Why is it proportion? Because I have no idea what mean would even mean in this case. Is that right? Right? But yeah, what is the mean here? See, the problem is that the proportion is actually a mean, right? But they're not really explaining it that way. So in this case, we just want to separate between mean and proportion. This is obviously proportion here. So I write proportion and I write proportion. The null hypothesis always equals something. The alternative, we have to read the question to see what it is, but you should determine the alternative first. So what is it? What is the alternative hypothesis in this case? What do they want? So, right, P less than 16 over 10,000, right? Does that make sense? I'd rather just leave it. So then we have this, right? Why would we be saying this? Because then someone somewhere is claiming that 16 and 10,000 fireflies is somehow important, right? And then I do my observation and then I start seeing that that's not the case and I actually see less. So then therefore I want to try and prove that. Is that right? Question here? All right, what's the next one then? This is definitely means is correct. But don't do null first. Do the other one first always. Doesn't really. It really doesn't matter very much, but slightly easier, I guess. All right, so then this is equal to this. This next one is a decent example, honestly, for a reason why you would have to do a two-sided test. In this case, they're saying that they're making some beer kegs or something in these refrigerators or whatever. Sorry? Yeah, because they want it to be exactly 48 degrees here, right? So we need to test whether or not the mean is equal to 48 degrees. If it's less than 48 degrees, that's not good for this stuff. And if it's greater than 48 degrees, that's not good for this either. So therefore, we actually want to see if it's not equal to 48 degrees. So that's a reasonable example for that. Any question with this? All right, so that should be pretty easy. The only reason why I'm going over this is because this is practically all you have to be able to do this stuff on the calculator. Okay? Like once you can establish what the alternative hypothesis is, effectively, everything falls into place. Okay? It's like a joke. All right? So we'll do it in a second. Well, okay, so the thing is when they start saying this, well, we start another, oh, by the way, I'll say it later. I shouldn't say it now. But this is saying like you really don't know if it's larger or smaller, right? So then the thing is like another way we can explain why you end up having to sort of reduce the alpha to alpha over 2, right? Is if the result ends up existing on the far right side, right? This time, you get some sample average, these refrigerators, we get the average ends up being on the far right. Does that make sense? We don't actually know that that should be happening, right? So next time, it's just as likely for it to appear on the other side. Is that correct? Does that make sense? Do you get what I mean by that? So then, you understand what I'm saying, Zora? So then the thing is that if you have that type of situation and you end up getting something on this side here, right? Then next time, really, we could be on that side also. Is that correct? So we'll explain this in a second, but we call this thing the p-value here or whatever, which is the probability of result at least extreme is the sample result given the null hypothesis is true. We'll write that down though. This thing here, in this case, you just want the p-value to be less than alpha usually, right? But now alpha is split to both sides. Then we start saying the p-value needs to be less than half of that. Does that make sense? Or you could start saying that 2 times the p-value needs to be less than alpha because we need to double this. Does that make sense what I'm saying? All right, I'll say that again in a second though, okay? All right, so let's just mention this again here or whatever. If alpha is 0.1 for a two-tailed test, then I would put 0.05 on this side, 0.05 on this side. To determine the critical z-score here that's necessary to reject the null hypothesis, right? We would have to say that z of 0.05 is 1.645 approximately, and this one's negative 1.645. So the rejection criteria would be this. Does that make sense? What? It just happens all the time, and then the thing is they're always the same values. So then you just never. Well, first of all, 95% is just you just know it, because the problem is that when it's 95%, you're supposed to know from the empirical rule and all that other stuff that you learned that this 95%, this is z. They say z is 2, and this is z equals negative 2. Now that's not exactly correct, obviously, right? It's approximately 1.96 or whatever. So the thing is but this is an easy thing to remember, and it's relating things to your empirical rule from before, 68, 95, 99.7, right? So that's the thing with that, okay? Now, there's usually like 3 main types of confidence intervals or alpha levels or whatever that people start using in a lot of cases. One of them ends up being this one, and this one. So since these just constantly end up occurring, you just do it a couple of times and you end up remembering the values. Does that make sense? Yeah, it's not like you need to sit there and memorize them. Okay? Question with this? You could just what? You could always do a lot of things, but why would you? All right, so now if alpha is equal to this, what would I write here for the decision criteria and the critical level? Yeah, but what is this one going to be? Second one. How would I do it? What do I write? Z, and then what do I write here? What would, for this value right here, what would I have to write down there first? What's the alpha? 0.95. Okay. This stupid notation is the only notation when something means to the right. Does that make sense? So like if I write Z alpha like this, right? This is the critical Z score for area alpha to its right. In other words, it means that's alpha. Does that make sense? That notation. Does that make sense what I'm saying? All right. All right. Okay. So then the unfortunately this is the way everybody writes it. So then like you always see like Z alpha over 2, T alpha over 2 and stuff like that. That's what they're writing. All right. So then this here, Z, it should be Z 0.95. Is that correct? So if we wanted to determine Z 0.95, I would have to do inv norm of what? How would I determine this? Inv norm of what? 0.05. This function, inv norm, is like sort of like the inverse of the CDF function. Is that correct? I'd mark that wrong on the test because the thing is I'm going to ask the person what the actual function what they have to type in the actual function. So then based off of this thing, the only answer to this right here, if I just ask that one number right there, is 0.05. But it is. Because the thing is that so like I've said this before, but if you use any type of any of these programming languages, Excel, any of this stuff, right? And then you wanted to go and calculate some of this stuff, they're all written the same way. Everything is always written in terms of CDF. Does that make sense? And then everything is always written in terms of the inverse of the CDF because the CDF is an increasing function. Does that make sense? So it's 1-to-1. So then the thing is that so like for instance here, let's say I wanted to do the inverse of the chi-square distribution. So Q, say one more time. Let's just think about it let's just think about it this way, okay? So like there's a bunch of probability distributions, right? Right? So then given some probability distribution, you have some probability distribution, and then we say we start to find the CDF. So the CDF is going to be, let's say, something like that. Does that make sense? I need to then, given some sort of percentile, right? So given some percentile P, there would exist some place here that would be some X value from the distribution that would then be in that percentile. Is that correct? Okay. So the idea is that all the functions sort of work this way. Okay. CDF takes a value and then gives you its percentile. Is that right? The inverse function then for this, right? If this goes from X to Y, the other one should go from Y to X, right? Then this one is going to be, you have to give me the percentile or the area, and then it's going to provide you the value. But then the thing is that this has to be the percentile or area to the left of the position. Does that make sense? So anyway, all the functions are generally written this way. So that's the reason why I'm saying it that way. Why is the Z backwards? Or why is that one notation backwards? So it's a reasonable question, actually. Okay, so then the thing is like when you're surprisingly, so then when you're I'm just drawing a normal distribution, but it doesn't have to be that type of distribution. But let's say you're constructing a confidence interval. All right. Usually, are you gonna listen or no? Yeah. Usually, what's gonna happen now? Usually, what's gonna happen is that you need to determine what that distance is from here to here, right? Okay. So then we refer to that as what? E, right? Margin of error. Okay. Where E is equal to the number of standard deviations away times the value of the standard deviation. Does that make sense? All right. Now, this thing here, right? If you wanted to determine this value, right? You're probably going to do the right side first. Also, you're probably going to sit there and try and test if it's greater than first, or figure out how to do that first. Okay. So then, in terms of the theory, what you would do is if there's an alpha that's written over here, right? There's also things that are called one-sided confidence intervals. You don't just need to have two sides. Does that make sense? All right. So then if I was trying to construct this interval, right, I would need to determine the number of standard deviations it needs to be away times the value of the standard deviation from whatever the distribution is. The number of standard deviations away for a normal distribution, we refer to that as Z alpha here, because this then is going to be the amount of standard deviations for this particular critical region here. Does that make sense? All right. So I think it does make sense. It's just, yes, that's correct. All right. So now we should actually do a problem. Okay. So no, this will be easy. Well, this will be very easy with the calculator. I'm going to do it first time without the calculator. Always first time without the calculator, second time with the calculator. Also, we will be using the confidence interval method to solve this as well. Okay. I really like the confidence interval method because it actually like sort of makes more sense. All right. But they're directly related to each other constantly. Hypothesis test and confidence interval. So this becomes, wait, did I forget to do a question first? I would like to do this question first, actually. All right. Use the given information to find the, no, actually, we can't do this yet. I haven't told you what p-value means. Great, I just erased all that for no reason. All right, let's go back to where we just were, sorry. All right, I don't feel like rewriting this, so I'm just gonna make it play it again. All right, so let's read the question first. The claim is that the proportion of accidental deaths of the elderly attributable to residential falls is more than 10%. The sample statistics conclude not n is equal to 800 deaths of the elderly, with 15% of them attributable to residential falls. Okay. All right. Now it doesn't tell you the directions here. It should say test the claim. Does that make sense? Does that make sense? What I'm saying? All right. Now, this is sort of and people explain this thing in different ways. When I was originally explaining this, I was explaining it as a four-step process. All right. I like thinking of it as a four-step process because that generally will apply in other situations when you have to do these same things. All right. I'll show you. So then so now what are the four steps? All right. So the first one is going to be hypotheses and assumptions. The next one's going to be test statistic, which is going to end up being Z or T. The third thing is going to be p-value, which we really haven't gone over yet. And the fourth one's going to be drawing a conclusion. Does that make sense? All right, which is kind of the main part, right? Exactly. All right, now, where should we start? What would you say? Anybody else have a suggestion? No, but like, okay, what does that mean though? What do we do though? We must determine our null and alternative hypothesis first. There's no way we can do anything until we do so. Is that correct? We can call it step 0 if you want. Does that make it better? Then we can call the next one step 1/2, and the next one after that step 1, right? And then the last step will be called like step infinity. All right, so then the all right, so we have to come up with our null and alternative. So what would that be in this case? That's the alternative, right? So that's correct. You need to determine it's a proportion, right? And then in the question, they're stating it needs to be more than 10%. So that's what we're going to have to go with because we kind of have nothing else. And then you always need to assume something in the null hypothesis. So it must be equal something. Does that make sense what I'm saying? Right? So then, because what we're saying with these things is, right, assuming that P is equal to 10%, given the distribution that could occur with the sample estimates or P hats, right? There ends up being a range of values that could be possible. Is that correct? Right? And then by random chance, is our observed value actually significantly different from the assumed parameter? Is that correct? All right. So here now, there you do have to satisfy assumptions with these things, and the assumptions are the same as what they are for the confidence intervals. Do you recall what the assumptions are necessary that need to be satisfied here? What would you say? What are they? Anybody? I don't know. You need the assumptions. Well, you obviously need to be randomly selecting things. All right, but that's obvious. Any sample should be randomly selected. Otherwise, there's no point to do any of this. All right, so it should be randomly selected. Is that correct? Sorry? Okay. You don't have to really do that here, but what there is something you do have to do. Independence of trials is really just more based off of how you're sampling things again. So as long as you're randomly selecting these things in an independent fashion, it's going to be satisfied already. Does that make sense? There are no real trials here. What were you saying? Say what was on? Yes, but the problem is that we're not really doing mean here, right? So then but that is still correct though. Okay. So the thing is, but they don't want you to say it that way. Okay. So what they want you to say is that, well, they want you to talk about NP and NQ. Does that make sense? What does N times P mean though, first, just to remind ourselves? Expected number of successes in this case, which in this case, the success is of someone passing away for a residential fall in this case, right? So that success. All right. So then, and then N times Q is the expected failures. Is that correct? Right. That's all right. So these calculations are usually okay. Now, the real rule is that this is supposed to be greater than 5. In a lot of places, though, it says greater than or equal to 10. Okay, that's just a tighter bound so that the normal distribution and binomial distribution end up looking similar. I think so. All right, then this would then imply that p hat would follow a normal distribution. Does that make sense? Approximately normal, but it's a normal distribution. Does that make sense? Right? Technically, there is no such thing as anything that is truly normal. Everything is approximately normal. So stating approximately normal is kind of redundant, to believe it or not, but nonetheless. Yeah. So then this p hat normal, right? Now the thing is you have to think about like what the normal distribution would be. Once you can establish what the mean and the standard deviation are, though, then always we're going to be able to answer all the questions. So in this case, y is the mean p. Yeah, why? Why is it p though? No, I mean this is a number. This is a number. I know what the number is and stuff like that. Why can I say that? Yeah. I'm asking you, obviously. You get it? That's what I'm asking you. I'm saying I know. I'm saying we definitely know actually. Yeah. We must assume the null hypothesis is true. Is that correct? So since we're assuming the null hypothesis is true, that means then we're assuming that P must be equal to 10%, right? Therefore, P is 10%. Does that make sense? Right? Then the thing is this is the reason why we can actually state what the distribution of P hat is, because now we can say exactly what P and Q have to be here. Is that correct? Does that make sense? Does everybody understand what I'm saying? I don't know why it's not there yet. It's just not copying. But this is going to be like this is 0.1. This is 0.1 times 0.9 all over 800. Does that make sense? Now we have everything. So that means we can calculate everything. Is that correct? All right. Sorry. Technically, like 2 and 3 are sort of like can be combined, really. Just finish this. If we do the confidence interval method, it more or less moves directly to step 4 right now. So then all right, now we need to do test statistic. What does test statistic mean? Again, it just means how many standard deviations away, right? Z or T just means the number of standard deviations away from the mean. Is that correct? It's very important to remember that. All right, just to be able to say that every time. It's helpful. All right, so I'm drawing a little. Oh, so what should it be? Z or T? And why? How can we select whether it's Z or T? And then why would we be able to select that? So the thing is that what you need to remember is Z is equal to what? X minus mu over sigma. Is that right? Right? That means you need sigma. Is that correct? The only time you use T when you don't know sigma. Does that make sense? So in this case, we actually sigma is actually known. Does that make sense? Like this is like the sigma. Does that make sense? All right. So we're good. We actually have it. We can do Z in this case. Does that make sense? So we determine number of standard deviations away from the mean. All right. So we need to label this thing. I should have just asked you how to label it, but I guess, oh well. So then the mean here is 10%. Is that correct? Next thing you want to do is label your sample result. In this case, we would label that as p hat. Is that right? The sample estimate, right? Does that make sense, guys? And we want to see if this is significantly different from that value. Is that correct? All right, well, how are we going to do that? Well, we're going to do it the same way we've always done this, right? We're going to calculate the z-score. Does that make sense? The z-score is equal to the value of the in. He knows. He's just. So the z is equal to the value of interest minus the mean divided by whatever the value of the standard deviation is. But we have all of these things. The mean is whatever this is. The standard deviation is whatever this is, right? Does that make sense? All right, so then, wait. All right, does this make sense here, guys? P hat is the value of interest in this case, or the sample value, right? The mean in this case is P. We need to determine the distance between these 2 points here, right? So it's 0.05, and then we need to divide this by the value of the standard deviation, right? Well, that's what we're doing right now. So I got 4.714. This is actually not that hard to calculate, believe it or not, because it's 10%, 90%, and then 800. So then like the hundreds cancel and stuff. You can actually do it not that bad. Yeah, that's exactly what it is. Yeah, it's not that bad. So then you just leave it in terms of radical. Ah, you lost. Okay, so then this, all right, so we get this. Does that make sense? Does that make sense, guys? All right, now we have to calculate p-value. Now I'm going to actually try and write down the definition of p-value here, hopefully. The probability of a result, at least as extreme as the observed sample result, given HO is true. Does that make sense? How would I do that, though? Why does step 2 tell me how to do step 3? That's pretty much the question, because otherwise you're not thinking about the process here, right? That's correct. So this should be actually pretty simple now. Okay, so then let's go. So then this thing here, right? So now we need to calculate the probability that p hat is greater than or equal to 0.15, right? But that's equivalent to calculating z is greater than or equal to 4.714. I really should not have rounded this. There's no reason to round this here. Does that make sense? I did later. Okay, so then we would have to do normal CDF. We would have to do this. Does that make sense? Okay. Now again, this is just teaching you what to type in again, right? This is the far right value, so that's like infinity. This says normal CDF. Look, it says it right here. I don't know what you're talking about. That's so anyway, normal CDF here. Normal CDF, right? You can just make it calculate the whole thing for you. And then this is just what? This. Does that make sense? Now I put this number here just because the thing is like a lot of times teachers will just say like put 10 or something or 5 or whatever. But technically there's going to be cases where that's not going to work at all. Does that make sense? So this is like one of the largest numbers in the calculator. So that's why I'm using that. Does that make sense? So then we get this. Then we get this. Does that make sense? All right. Now the only thing is again, you can remember. I don't even feel like typing it. All right. So we get this value here. So what does that mean? At least as extreme as that value, right? So now we're taking all of the chances of anything more extreme than this. We're calculating all of that. And then we're saying that probability, given the fact that we're assuming that the proportion is 10%, right? The probability of getting something at least as extreme as this is this number. What is this number again? What does this mean? Like, what is this? What's the 10 to the negative 6? What is this? Yeah, but what is the number? Like, not with the 10 to the negative 6. How would you write this without 10 to the negative 6? What is it? Yeah, so this is approximately, this is like what? You have to move the decimal place 6 places left. Is that correct? So it'd be like 5 zeros, then a 1, right? So then the thing is, this is literally 1 in a million. Is that correct? Right? 1.216 in a million. Is that correct? All right, now we have to draw a conclusion here, right? So how are we going to draw a conclusion? What would you say based off of this? No, but what would you say based off of this? What conclusion should we be drawing? Why? So the thing is this is like, you shouldn't just like see events that are all the time that are like 1 in a million chance. Is that correct? You could. That's why we can only say that, like, we can never prove something with this. We can only suggest things, right? But the thing is that like this happening here should not be very probable. Is that correct? Right? So then the only thing we assumed is this. So that now leads us to believe that there's possibly an error there. Is that correct? So then with a high probability, right? All right. So this is how we make the decision criteria, right? We reject the null hypothesis if the p-value is less than alpha. We fail to reject the null hypothesis if the p-value is greater than or equal to alpha. This is how we determine every single time. This question here, though, that I'm stating, like rare enough, not rare enough, that's what you have to constantly be asking yourself when you're doing this, right? If you get to the end here and you ever get confused, all you need to ask yourself is this rare enough? Does that make sense? Is the probability small, right? So you just remember P is low, reject the hoe. Does that make sense? P is low, reject the hoe. Does that make sense? All right. So then the question with this, I don't really know what that means. Thanks. I think that's a good thing. I don't understand what that means. All right. So then this value is definitely small compared to 0.05. Why am I using 0.05? Because they really did not provide me an alpha level. And we said previously that if they do not provide you an alpha level or some sort of level of things being unusual or significant, then we automatically assume it's 5%. Does that make sense? Sorry? Sometimes the phrasing of these things, they'll write it that way, like level of degree of unusuality or usuality or something like that. They'll start saying this. But it's like the problem is like students sometimes get confused between significance being unusual and stuff like that. So that's why I'm just stating it again. Say again? That's a good question. All right, so then so there's significant evidence to support the claim that greater than 10% of the elderly deaths were attributable to residential falls. So all you say here is because p-value is less than alpha, we do have significant evidence. Does that make sense? So there is significant evidence to support the claim. And that's really it. Does that make sense? You're rejecting the null in favor of the alternative. So you're supporting the alternative. There's the only thing. There's no other way. There's no other way that people are supposed to be writing hypotheses. No one understands what that means. It's absolutely ridiculous to say it that way. Like if I say, because like this, if I say to you, like, right, we do some sort of engineering presentation, you do some research, you do whatever, and then if you do this research and you sit there and you come up with your experiment and you draw your conclusion, right? The whole point of the final sentence here is so that the person who's reading the paper doesn't have to read the rest of it and they can still understand what the conclusion means. Because most people won't understand the hypothesis test and won't understand what these things are saying. So the point is that they need a practical statement that they would be able to use to summarize the entire thing. And you think it's a joke, but the thing is, I've sat there before with like a room full of engineers, and you go through these things, and there's like maybe one or two in the whole room that understand what you're actually saying. And then you get to the end, and then you're like, you summarize it, and then they all start shaking their head like they understood the whole time. You know what I mean? But if you don't say that, like they're completely lost. And these are people that are trained. Correct. Correct. That's exactly what it is. So like the thing is like you go through the entire paper, you write everything perfectly, you write everything well, you explain everything, and then you get to the end and then you re-summarize it in some dumb way so that if the person didn't want to read it, they could do it. Okay. So the question with this? I don't believe in divine. No. No. All right, let's do the same question, but use the confidence interval to solve the question. I feel like this actually makes more sense, believe it or not. All right, so then so null hypothesis, alternative hypothesis, right? Can't change, obviously, it's the same question, right? And it's kind of only like 3 steps, I guess now. All right, so now the thing is like the confidence interval, we're going to create a confidence interval about p hat to check if p is contained within the interval. Does that make sense? So then we construct a confidence interval about p hat, right? All right, great. The only problem is though that you must construct the right size confidence interval. Does that make sense? Okay. If you do not construct the right size confidence interval, you're not matching up with the significance level from the previous test, right? So then, sorry. Again, every time it doesn't tell you a significance level, you must assume it's 5%. Because statisticians just start saying things are unusual when it's less than 5%. It does make sense if you start thinking about so let's say we're going to play a game, okay? Let's say we're going to play a game, you and me, all right? All right. And then the thing is, but you're not going to learn how to play. I'm not going to learn how to play. And then, but we're still going to play. Okay. Who's going to win? No, you versus me. Who's going to win? Me. I'm going to win. Correct. Okay. So then no, but seriously, if I don't learn how to play and you're not going to learn how to play, right? Then what's going to happen is that we really should have the same chances of winning this game, right? Yeah, but not if I don't want to try. I'm assuming you don't. I just said that. This is hard. So then no, but my point is that if you can't say anything better, right, and you're saying there's 50% chance, right, then the thing is that if that was to become as small as 5%, that's a factor of 10, right? But that's significant in terms of an estimate for a probability, right? That's an order of magnitude, right? So the thing is that when you start saying this type of thing, they use this sort of rule of thumb. Okay. Now, in reality, when you get to all of these different hypothesis tests and all that kind of thing, in each different situation, there's a different alpha level that's required based off of literature and research and all that kind of thing. And there's an established level that people accept. It's like the burden of proof necessary. If you're doing something with medicine and there's a cancer patient and all that kind of thing, I think you might want a higher burden of proof. If you're doing something with the heights we were talking about before, maybe it doesn't matter as much, right? But the thing is like this is usually established through research and stuff, right? So anyway, we have to come up with the right size confidence interval. All right. The simplest way to think about it is you just start constructing a confidence interval here that needs to end directly at that start of that region. Does that make sense? Does that make sense? If you think about it as 2 separate normal distributions, it should be somewhat obvious. Because like if we imagine that p hat is being centered here, right? And then there exists another normal distribution, which is the real one, really, that's like over there for p. Does that make sense? Right? Then for this to be equivalent to each other, if we imagine that they were completely overlapping with each other, right? Right? Then if they were completely overlapping with each other, then if alpha had to be 5% over here, well, then the confidence interval should therefore end at the same place that rejection region starts. Does that make sense what I'm saying? Does it make sense or no? Yes or no? All right. So then so effectively all I have to do is determine the correct confidence level. So how do I determine the correct confidence level here? This is 90% because that would be 5%. That would be 5%. Does that make sense? No, if this is 5% here, right? If this is 5% here, right? Then because because our original hypothesis was greater, and alpha then has to be put on the right because it's one to right tail test, right? So then this thing here, if we want to do this, then this by symmetry, this would have to be 5%. Therefore, this would have to be 90. Is that correct? All right. So then here we have to construct a 90% confidence interval. Does that make sense? All right. Let's go back for 1 second and just do this with the calculator because I need to show you how easy this is. So we click tests. Which test would I pick? Which one do I pick? No, we don't have two samples. We only have one sample. So you only can choose between 1, 2, and 5. Does that make sense? One prop because that's proportion. Does that make sense? You could do it with Z also, but then you have to actually type in the standard deviation. So then this proportion, so then P naught is 0.1. How do I determine what X is? X is the number of successes, is correct. So this is 0.1 times 800, right? N is 800. This we just put greater because that's what this says here, right? This is such a joke. You're going to love this. So then you click this. Whoops. No, I just typed it wrong somehow. 0.1. Oh, I'm sorry. X should be 15% times 800. That was stupid. Because the sample is 15%. Is that right? That was dumb. That was a big mistake, actually. All right. So then we get this, but then it immediately gives you this answer. It immediately gives you this answer. We're done. Does that make sense? All right. Now, when you come to this one, if you want to do this, the only problem is the calculator does not know what the confidence level is. But this calculator is actually really nice. It's like a teaching calculator, and it shows you stuff while you're doing it. So if you click on this one now, one prop Z test, or interval, excuse me, right? Now this, I didn't type this in. It just followed through from the other one because it knows the two tests are, the interval and the test are connected. Does that make sense? So then this comes in here. This is wrong though. I need to select the right level. So then I select 90%. Then I get this. These are the numbers I've just written right here. How would I draw the conclusion based off of this? No. Don't say assumed p-value. First of all, p-value means probability, right? Proportion and p-value are not the same thing. Does that make sense? All right. Okay, that's good. So the assumed parameter p, right, is not contained within this interval. Does that make sense? Since p is not contained with this interval, it would therefore lead us to believe that p is greater than 10% probably. Does that make sense? Question? All right, let's end there.